Professor Huckabee here. This is a lecture from last spring, and it covers the last of Chapter 5 and just starts Chapter 6. I hope that you all enjoy it, and here is your to-do list. So do your homework assignment, finish Chapter 5 and start reading Chapter 6. Start working Chapter 6 problems as well as Chapter 5 problems, and come to the help sessions and videos. And with that, I wish you all the best.
Which one is this? I think it's in this pile. Yeah. Oh no, wrong pile. There we go. All right, so going back to a slide from before about the diastereomers and the stereoisomers, something else weird about chirality kind of comes out. If you have a molecule like this one with two chiral carbons, let's do it in blue. I like blue. There we are. Two chiral carbons. Again, you can draw the structures for these, but I prefer to just show you because it saves me time, and my drawings aren't always that great. Here you have four possible stereoisomers. You have a pair of enantiomers where one oxygen is up and one is down, and you have a pair of enantiomers where both are up or both are down. But I want you to picture the isomer where both are up in your mind right now. Try and envision that looking straight across the CC bond here, both up. And in your mind, I want you to flip it over, just simply over, like a pancake. I think you'd find that that's the exact same molecule as the one down. Even weirder, not weirder, as a consequence of this little mind experiment, this molecule, we're again using the Haworth projection, has a mirror of symmetry that maybe you weren't expecting here. It has a mirror plane inside the molecule, meaning that if you reflect this to that side, it's the same molecule, right? We have been dealing with separate molecules that do this before, but now we find it in one. And because it has a plane of symmetry, we call this reflective symmetry. Any molecule that has this reflective symmetry is not chiral anymore because it doesn't have an enantiomer. It and its enantiomer are the same molecule, so it's not chiral. Therefore, we have a different word for it, which is up here, meso. So remember I told you that there was a mathematical formula you could use for where two carbons, or the number of chiral carbons gave you the number of possible enantiomers. I think it's record time that I gave you a rule and the exception one slide after the other. Because this is the exception, and it does happen. If you run into a case where you have a symmetry, or you have a reflective symmetry in a molecule, then those two enantiomers are meso and are actually not chiral at all. Oh yeah. So kind of now so this seems a little fragmented, all these things, but the field of chirality is so broad, and there are so many types of isomers that it's really kind of like show you an example of an isomer and how things are chiral, move on to the next one. So the next one we're going to talk about are sugars, another bioactive molecule. They're in the old days, back when they knew something about organic chemistry, but they were still learning. There was a lot of different ways to draw molecules. We've talked about projections a lot. Newman projections, Haworth projections. Another one that was designed specifically for molecules like sugars is called a Fischer projection. And in this projection, the whole point is that you have these crosses that signify the things on the left and right are coming out towards you, I guess it would be out towards you, and the things on the verticals are going away from you. So try to imagine that in your mind. Every time you see a left and right, that's going towards you, and everything on the verticals are going away from you. So when you see a projection like this, that's obviously a lot easier than trying to imagine this weirdly curved structure here, because you can use this rule in your mind to connect it a lot faster. And the reason why we still talk about it today, even though it was probably, I don't know, I bet it was first published like 80 years ago or something. The reason why we still talk about it is because it does make finding enantiomers and diastereomers pretty easy. Here on the bottom right, you can see the case of two enantiomers because they are mirror image, non-superimposable. Do you see that if we put just a mirror in between those two, they would be the same molecule? So they are enantiomers. But on the very right, these two molecules, if you drop a mirror in between them, they are not mirror images, but they're still non-superimposable. So they're still stereoisomers, they are just diastereomers. And your book gives a lot of different examples for how to find these. As is the case for the other isomers, I would suggest that you do all the problems, at least like in the textbook section. And you might be rewarded with a test question if you do those. Like, I would bet that I find test questions in the book that look interesting. That I pull test questions from the book because I did it last test. So I don't know why I wouldn't do it this one too. So now I have a question for you. We talked about a bunch of isomers, but let's scale back to what we talked about in chapter 4, which was conformational analysis of butane. You remember butane? It is 1, 2, 3, 4 carbons. H, H, CH3, 2 H's, and CH3. So if we just learned you can have chirality if your molecule has a non-superimposable, non-mirror image partner, does that mean that if you draw a Newman projection of butane, like this, and you compare it to a conformer, does that mean that these are diastereomers? Because I don't think we can superimpose them. Oh yeah, I really had fun with that one. There we go. Okay, let's just call this one big H. How about that? It's a big, ugly looking H. Oh, yeah, and there's this. Yeah, I just got too excited. These are not superimposable, clearly. And they're not mirror images. But are they diastereomers? This one has an answer. I'm not just throwing it out through the wind. Looking for some nodding, some heads shaking, and disbelief. You can run out of the classroom if you want. This is just blowing your mind. No. These would be diastereomers if you could be sure that they weren't going to just rotate back out of where they are right now. Because remember, in conformational analysis, we were talking about how these guys can rotate freely all around, and there are energy costs associated with going across this H and across this CH3, but they could still rotate as long as there was enough energy, right? If there's enough heat, they could just be freely rotating, and so you would never actually find the conformation, or at least not for very long, that would be chiral. You would never find the diastereomeric pairs here because they're just basically always moving. If you could freeze them down to like absolute zero or something like that, and they didn't have the energy to move around, then those would be chiral. Because they would be physically locked in place, and they would be non-superimposable, non-mirror images. It's a big distinction because now we're in the realm of talking about things that are not as easy to think about as if it's a chiral carbon or not. It's easy to look at a structure and say, oh, this thing has 4 unique substituents, it's definitely chiral. Now we're talking about finding molecules that are locked in place or not, and talking about if they have a diastereomer. And right now, in modern organic chemistry, this is actually a huge field because people have found that there are many types of molecules that are conformationally locked that we hadn't thought about that often. One good example is when you have 2 benzene rings that are connected directly to each other, and then something in the position next to that connection. Because when you try to do this rotation, this figure really does it better than I could, I think. These substituents here on the top, the bromines and the iodines, iodides, are so physically large that you cannot get across them. If we were to make a conformational analysis of this molecule, you know, where energy is increasing, and we started at that perpendicular state on the left, getting across would fly off the paper, and you wouldn't actually see the energy that it would take, because it's not really possible. Some really smart chemists have used molecules based on these atrope isomers, that's how you would say that, atrope isomers, to do chiral reactions because they're very stable, they can't do anything, they're conformationally locked, and if you could imagine putting some useful catalyst or something onto one of these positions, now you have something chiral in addition to doing useful reactions. We'll talk a lot more about reactions later, but as an aside, having this part talking about chirality and different groups that are chiral might not seem that important, but chiral molecules are really hard to synthesize because if they can only come from something that makes them chiral, they have to be forced into chirality. For instance, this molecule on the right has chirality. So, as I said before, if you had a catalyst attached to this molecule and you perform some reaction, like let's just draw something, like you had some reaction, you took formaldehyde and you attacked it with something, I don't know, we'll say we attack it with oxygen, okay? Let's say you attack it with oxygen, a negatively charged oxygen. Do a reaction here. Oh, I left off some lone pairs. That's fine. Oh, I don't want that to be CH. I want this to be like D for deuterium. No, I don't want to do that to you guys. Oh no, I'm coming up with this off the cuff. It's not as easy. There we go. We'll just say this is what happens. So we do this reaction, and what we end up with is this molecule here that, if you look closely, should be chiral, right? Because it has a carbon with 4 unique, that's an asterisk, 4 unique functional groups. However, if you notice, I did not put any bonds or wedges there, did I? Or wedges and dashes there, did I? Because if you do this reaction without some way to make it chiral, you will get one enantiomer and the other in the exact same proportion. So think about this. This one, again, also doesn't have an answer, but it is something to think about, especially going forward in this class and the rest of your studies. Our bodies are made up completely, not completely, the stuff that makes our bodies work utilize chiral molecules. Enzymes in our bodies work based on chiral molecules. But chiral molecules can only exist by being made from other chiral molecules. So where do they come from? How do you make them? Where, why, and how? All right, boring chemistry again, real fast. Allenes. Another weird one. Imagine a molecule. Yeah. Like this. I've drawn it this way for a very specific reason. This carbon, its substituents are like this. Whoa, that was really close to my mouth. But the other one, its substituents are like this. They are physically locked because of the way that these 3 carbons are locked. There are how many pi bonds in these 3? How many? I see, yeah, good, 2. There are 2. 2 coming up physically, but this carbon has 2 double bonds, and he has 2 horizontal pi bonds. So yeah. Okay, it's every 30 minutes, right? It's got to be every 30 minutes. That's like an alarm system. Maybe we should stay till 6:30 and really make sure that we know if it's right or not. No? Okay. So these are locked due to the pi bonds. One is physically vertically oriented, and the other is horizontally. So those are locked just due to the combined powers of chemistry and physics. So those molecules can also be chiral. If you put this one in a mirror with this one, oh yes, okay, so it does it twice now. Maybe we'll get to the point where it does it like 100 times every time, and I'm just constantly over here. Yeah, so if you write the mirror image, these are also clearly non-superimposable, right? They are mirror images, but they are non-superimposable, which makes them chiral, even though it's not chiral in the same way we were talking before. I think you could almost see them superimposed this way, right? It doesn't work. So I think that's the last group, except for this little fun fact. Going back to alkenes, those fun alkenes we started with, and I told you we were going to come back to them later, depending on if they are on the same side or on the opposite side, you call them E or Z. E for if they are on the opposite side, and Z for if they are on the same side. That's as simple as it gets for alkenes. You just remember, same is Z. And I learned a really good way to remember it from an old professor. And I think in this case he had to be old to actually to give me this fun fact, because when he learned organic chemistry, he was required to also learn German. German used to be the required method of communication for organic chemistry, actually. They were the world leaders in organic chemistry, and if you were going to study it, you had to learn German, and that's where these two things come from. E is for entgegen, which doesn't have any bearing to two things being on the different sides, but Z stands for zusammen, which sounds like same. So Z, zusammen, zusammen, same side. That's how I always remember it. That's it for that. We're really getting close here, guys. Oh, right. Okay, so this is going to be good. We have 15 minutes. We can definitely close out this chapter in 15 minutes to get chapter 6. Oh, yeah, easy. And we'll get into chapter 6. All right, good. We're so good, guys. All right, so in that beginning question, I asked you, how do you separate those two molecules? This is a huge thing that we deal with in chemistry. There are whole courses of study in graduate school you can learn about how to do precisely this. I asked about that lab where you did the recrystallizations in the organic chem lab course, because one of the ways to do this is through chirally, what's called resolving enantiomers through crystallization. We say resolving because you take a mixture and you resolve them into their separate entities. And so here, when you do this, you take, for instance, these two nitrogen-containing compounds that have a chiral center, and you use acid-base chemistry to protonate each of the nitrogens. Oh, now it's like really there. Okay, to protonate each of the nitrogens, and when you do that, you make a salt, a positive and a negative, and you hope that one of them crystallizes easier than the other. That's it. That is the basics of it. That's how hard it is to do separations of chiral resolving or of chiral materials, because otherwise, if they don't react differently or crystallize differently, there's no hope, because they boil at the same place and they have the same melting point. So again, about that weirdly philosophical question about where do chiral molecules come from, you could interact with these molecules in ways that are not just physical interactions. You could hope that the sum of very small, weak interactions due completely to the fact that they are chiral would help you to separate these molecules. And this leads me to what I think is probably the most fun and useful way to separate them. Maybe not the most useful because it's pretty expensive, but the most fun way. There's a thing called column chromatography in organic chemistry. Essentially, you load material at the top of this column, and you pour solvent through it. You kind of force it through with pressure. And as soon as those molecules get onto the column, they start a kind of race. So imagine, I don't know if any of you have siblings, and if you guys got the Zoomies at home and you would just run around and like chase each other through the house, just randomly. Or maybe with your friends, I don't know, maybe you did that. And somebody would get the idea that if you threw chairs in front of the other person, or if you ran around in a weird pattern, that you would be able to not be caught. Essentially, that's what this is like going through the column. Because the column is made up of very tightly packed silica microspheres. Okay, so you have like all these weirdly shaped physical things, and they all have pores and stuff, and they all also have groups attached to them, like protons and oxygen atoms that can physically interact with molecules. Because remember, in the very first lecture, we talked about hydrogen bonding, and how if you have a hydrogen bond donor, it's really just a proton, right? And acid-base reactions happen even if they don't happen to very much to one extent or the other. So you could imagine if you had a long column made with a lot of these microspheres, and you add up a lot of very small, tiny interactions, you could maybe have a very long separation between two molecules. And that's kind of what the chiral resolving chromatography does, is that instead of just having like a normal proton, now what you have is something with a chiral center that has a proton or something. And so now, based on the configuration of the stereoisomer, you can make a separation and then be able to very quickly and easily get one enantiomer or the other. It's not something that really gets covered much in organic in general. It's kind of an aside, but as far as cool stuff goes, it's something I like a lot. So really, is that it? Yeah, really that brings us to chapter 6. So before we move on with the last 5 minutes, any passing questions or remarks about chapter 5? No? Cool. All right, so chapter 6 starts off a little sad, because who likes to ever go back to your first physics or chemistry classes, right? Like, we're way past that now, let's just forget it. But we're going to delve right back in to the fundamental laws of the universe. In fact, number 2 and number 3 are really helpful in actual organic chemistry. What they say is, sorry, number 1 and number 2. First, energy can't ever be created or destroyed. So if you're talking about energy in a system, it's always the same. And number 2, the world is chaos, and it goes towards chaos constantly. It's the fact that you cannot stop. The universe goes towards disorder. Oh, I got all my papers mixed up in my excitement. Here we go. Okay. Yeah. Great. And this guy. Okay, so these are the laws of the universe, but that's not how we're going to talk about them. We're going to talk about them mainly in 2 very important vocabulary words. One is called enthalpy. Maybe you remember that from your most loved Gen Chem class. Enthalpy we talk about as a big H. We're also going to talk about, a little later, entropy. And that is a big S. Yeah. But first, let's talk about enthalpy. So enthalpy is, first of all, it's heat, right? If you all remember from your Gen Chem class and from other classes that you loved, it's heat. And what we're really talking about in enthalpy in organic chemistry is the energy it takes to break a bond. How do you go from this to this? That's an acid-base reaction, right? Except, well, yes, but also except no, because we want to talk about the energetics involved in organic chemistry now. This is called a homolytic bond cleavage. We have cleaved this bond, and we call it homolytically because the electrons from that bond all go to one atom. Okay? If you instead have the same reaction, I'm going to get this in for sure. Here we go. There we go. If you instead have the reaction where 2 single barbed arrows yield a neutral CH3 radical and an H radical, this is called heterolytic cleavage because one electron ends up on both atoms. There are different energies associated with each, but what we're going to talk about is the homolytic case because it's easier and it's much better studied. And the energy required to break a bond homolytically has a very special name, and one reason why we're going to use it, because there are just tables and tables and tables called bond dissociation energies. It's the energy required to break a bond homolytically. We can look them up. We can see which bonds are more stable by finding out how much more energy one takes than the other. But that's about all we're going to do. We're not going to go into it really in depth like we did, say, for acid-base chemistry. We're going to leave it there. But what you can do with enthalpy is that you can see an overall heat of reaction, because not all reactions are as simple as methane going to methane minus a hydrogen radical, right? Or a hydrogen or a proton. Most of the time they involve a lot more, so we're going to talk about them in respect to delta H degree. I don't forget what that's called. Anyway, this is the heat of reaction, the enthalpy of reaction. And that is where we're going to leave it for now.